click start. We can all see that it has started, so we are good there at least. And then let's all go to the class website and say that we are here. So please check in for the day, and then I think we're good to get started if there are no questions. Are there any questions that I could answer before we do? You all doing okay? All right, so a lot of different topics in this set of slides. We won't get to all of them. This will be a two-parter, but we'll get to some of them. So I want to first talk about logic. What does that mean? It's just a place where you can prove things. And what does it mean to prove something? In essence, it's where you show whether or not something is true or it's false. Okay? Truth and falsity. If you want to get fancy. That's what logic is, just showing whether or not something is true or false. And this is a very deep rabbit hole. Okay? It's a bit more complicated than just these two words. But then the first thing you might ask is, okay, we're gonna prove that things are true and that nothing is ever false. What does it mean to be true in that case? Because we have to get philosophical. This is a critical thinking class. So let's get philosophical. Let's talk about what does it mean for something to be true. All right. So that brings us first to a definition of the word statement. Okay. So a statement is something. It's just like an English sentence that can be true or false. So I'm kind of not yet getting to true or false, but we're defining statement in terms of it. You might also hear me call a statement a proposition. It's just a sentence, an English sentence that can be true or false, but it can't be both. This is kind of short for logical statements, by the way. That's the fancy term. Logical statements. And I'll abbreviate statements like that. You might have seen that before. But yeah, a statement, it's a sentence or proposition, is a sentence that can be true or false. It can't be both because that would make things unfortunate for us. So there are then sentences that are not statements, right? Like a command is not a statement. Also, this sentence is not a statement. This sentence is false, right? Why is that not a statement? Because if you break it down, well, there are only two possibilities, right? A statement could be either true or false. Let's see what would happen in either case. So if this sentence is false is a true statement or a true proposition, well, that means that it must have been false. Oh, that's kind of weird. It can't be both. So maybe it was false. Maybe that was the only possible interpretation that was correct. So maybe somebody telling me this sentence is false, maybe that must have been false then. Maybe that's how it can be a proposition. But if we were to assume this, in this universe, if this sentence is false, well, that means it must have been true, right? Because it was actually telling the truth after all. Do you see how we reached, in either case, boop, boop, we reached something called a contradiction. Do we all notice that? Whee. And in math, people like to put an exclamation point after the word contradiction just because it's extra weird. So yeah, there are some sentences that can be both true and false, and those are not the ones we want to consider, all right? Because those aren't statements. Those aren't propositions, all right? Any questions about that? It's a weird idea, I know, but we'll get used to it. And in math, or in some perfect universe, in some utopia, we would like to be able to prove every single true thing that there is about the universe and disprove or prove to be false all the false stuff. But unfortunately, that if you get into higher math, that turns out to not be possible, sadly enough. But it kind of leads us into what truth should maybe be. Should we define the word true to be all the stuff that we can prove? It seems logical, maybe. So this is where I tell you there's a bunch of different competing ways that people view the word truth. A bunch of different competing definitions of the word truth, in fact. I will go through a few of them here. There are plenty more than this, and they're meant for philosophers to philosophize over. All right? Let's talk about the first, correspondence theory. So all of these things that I'm telling you are people's interpretations of what it means to be true. This is very, very vague and philosophical, I know, but we'll get through it. So the first is correspondence theory, and they, the correspondence theorists, have determined, or they have defined, a statement to be true if and only if. You'll see that a lot in logic, the word if and only if. They like to say that. If and only if S corresponds to a fact. Okay? Interesting. Okay? Interesting. So only facts are true. Okay? And then you might have to ask the question, what is a fact? And that's, again, a very deep hole that we could go down that I don't want to go down. But that's their definition of truth, the correspondence theorists. So true things to them correspond with reality, things that they can go and observe. Okay, so facts, as in things that we could, like, here's me being Sherlock Holmes. I have my little magnifying glass, and I'm looking at something and confirming that, yes, this is true. Grass is green, things like that. All right? So snow is white is a true statement, usually, because I can go drive up to Shaver Lake or to the nearest ski resort and confirm that, yes, reality corresponds with this. Snow is, in fact, white. All right? So that's correspondence theory. That's one way of defining truth. And this came up on my Instagram. I thought it was funny. This is a great example of correspondence theory. Let me scroll down in my notes. So that brings us to the next one, another competing definition of truth. All right, the next one is called coherence theory, and there's several of these, but we'll use just one of them. So, to a coherence theorist, they define things to be true when they match other true things. Interesting. So it doesn't have to be something you can look at, but if you know something to be true and can compare it to something else, maybe you can get the truthiness out of that second thing. All right, so for example, math. Math we can't, like, view, but we know it to be true, right? The statement 2 plus 2 equals 4, that is a true statement, right? Because I can pick apart all the individual elements of it. I know what 2 means. I know what 4 means. I know what plus means. I know what equals means. And so therefore, if I put them all together and use my knowledge of those individual things, I understand that 2 plus 2 equals 4 is true, okay? That follows from all of that. And so that's one kind of coherence theory. Another kind of coherence theory is defining things to be true when they match the beliefs of the majority of people in society. And we know how much that could be an unfortunate definition. All right, so yeah, these are maybe not what you consider to be truth. But to some people they are. Isn't that cool? Bet you never thought when you were getting out of bed this morning that people might disagree on what it means to be true. Crazy. Okay, next one. Deflationary theory or redundancy theory. This one is extra vague. They don't even like the word truth in the first place. They think that it was unnecessary. They think that the word true is in fact redundant and should not be part of our logical vocabulary, because saying 2 plus 2 equals 4 is true is useless. Just say 2 plus 2 equals 4. The word equals implies truth. The word is implies truth. So there's no point trying to define truth because we didn't need it in the first place. Weird. And so that kind of gets around the whole question of what truth needs to be. And this is a question for the philosophers. As a computer scientist, this is as far as I have understood the theory in my mind. But we can discuss it more if you'd like. I'm just trying to give you some options to show you that people really do think different things. So yeah, feel free to shout out if you have something to say about deflationary or redundancy theory. But that's probably the oddest one in my mind here. So the last one, a fourth theory of truth, there are definitely more than these, is defined as this. Pragmatic theorists, they think that a proposition or a statement, right, those are synonyms, a proposition is true if it is useful to believe. Ooh. And so obviously our boy Mill would love this theory so much because it's all about utility, things that are useful. Those are the true things. And so if you look this up in the Internet Encyclopedia of Philosophy, they define pragmatic theory like this: beliefs that lead to the best payoff that are the best justification of our actions that promote success, those are the true things, according to the pragmatists. Interesting. So it doesn't have to be true in the way that we probably define truth in our minds. It just has to be useful for us, and then we can believe it. And that is truth to some people, to some philosophers, or maybe some non-philosophers. And so maybe a pragmatic truth to us would be something like, I will definitely get COVID if I go to the party this weekend, so maybe I shouldn't go. You don't know if that's really going to happen, but it's a good pragmatic truth, right, to keep us from getting sick. You see that? That's the idea. Any questions about this? Interesting stuff, I think. So you might be extra confused now, and I just want to pause and acknowledge that. We've been talking about what it means for something to be true, which is very odd of a thing to consider. So don't worry. Again, I'm just trying to teach you that there is no right answer to a lot of these philosophical, ethical questions that we're going to be talking about in this class, and trying to show you how many options you really have. Okay, when you're thinking about these things. So those are my theories of truth that I wanted to show you. Are there any questions about them before I talk about something completely different? Talking about pushing symbols around. Logical operations. We ready? All right. So I want to get into now Boolean algebra, woohoo, and truth tables. So we're going to have a lot of fun with these, I think, because they let us specify logical statements in a way that cannot be misunderstood, which is lovely. Things can't go wrong in logic when we use symbols, because English, I'm sure you've discovered by now, right? There's plenty of contradictions, and like two people can interpret the same sentence differently. Things can be ambiguous, and so you might be wondering, like, how can I make sure that there are no ambiguities in what I'm trying to say or trying to prove? How can I formally specify things that I'm trying to say and get across to somebody so that they don't misinterpret it, and so that we can agree on what we're saying to each other? Okay? So we have made a little mathematical language for all this cool stuff, and it's my turn to teach it to you. All right. So I have a question for you, actually, to start us out. Let's motivate this topic. So you got a waiter comes to your table, and maybe, I guess you just ordered coffee or something, and the waiter asks you, hey, do you want cream or sugar? Okay. And then a different scenario, you're talking to your mom, it's after dinner, and she says that you can have a cookie or ice cream for dessert. Okay? I would like you to get into peer instruction groups, humor me, introduce yourselves to each other if you're sitting next to new people today, and take some time to discuss the difference between these two ors in these two statements. Because I think if you think about it long enough, there is a difference between those two words, right? English. And try to write down the differences that you come up with in your little page right here under written ice. So please go there as a group. Figure out what group you are using the room map. Do you know how to do that by now? I can explain again if you'd like, but let me clear out all this stuff to start. Boop. So yeah, take some time to discuss how English can be ambiguous. Tell me what the difference between these words, the same word, this word or, in these two sentences is. So take a couple minutes, and we shall reconvene after you've had a discussion. Yep. Sure. Yeah, no worries. I can help you after we discuss, though. I want you to discuss with your group first, definitely. hear good words, remember to write them down. All right, that's like 2 minutes. Is that enough time to get something down? Let's take a look. Where do I want to be? All right, let's come back. I'll give you more chances to talk with each other. Don't worry. Let's come back and discuss. What's the difference between these? Cream or sugar, and you can have a cookie or ice cream for dessert. Let's see. First one is an and or in a question, whereas the second one is a true or in a statement. And or is, I think they're still right in there. That's all right. The first or is an offer of cream or sugar. Let's come back. I'll let you talk with each other again later. Thank you. So the first or, cream or sugar, you could have either one, or both, or none if you don't want anything. I like group 12's answer. And the second or is, your mom's telling you what's going to happen, right? You get one or the other, but definitely not both. That's how we interpret that. And I think every other group has written something similar. So great. We have just discovered another ambiguity of English. Awesome. This is why we would prefer to have some kind of mathematical way of specifying these so that we don't end up in this kind of situation where maybe somebody misinterprets mom as thinking that I could have a cookie and ice cream, right? Which is definitely not supposed to happen. So this one, yes. This one is you can have both or neither. And this one is you can't have both. Awesome. So, yeah, let's fix this. Let's introduce logic. So the first kind of or, the one where you could have both, is called inclusive or. See, everybody's allowed inclusion. The symbol, you could just write it out if you want to, but there's a logical symbol for this, and it looks like a little tiny V. Looks a little bit different than a V though, but that is the symbol for or. So if I have an A and a B, those are two propositions that could be themselves true or false. I can determine whether or not the combined A or B is true or false. And so think of A as like you can have cream, and think of B as you can have sugar. And these are all the possibilities of what could happen, whether or not this whole thing is true or false. And this thing that I'm showing you down here is called the truth table, by the way. This is our first one. This is a truth table. It shows all the different possibilities of whether or not something is true or false. All right? So this is A or B, or cream or sugar. And the idea for this inclusive or, is if you want to make it true, if you want to prove it, right? That's what it means to show that something is true. If you want to prove A or B, the whole thing is true, then all you have to do is show that one of the two is true. A or B or both are true, because that's all the different ways you can make it true. Does everybody kind of understand how to read this? It's a new table, but here are all the possibilities of when this works out, all right? So I could have cream or sugar. I could take both. A or B is true. I had the option. I could take just cream but no sugar. Then I could have cream or sugar is still a true statement. I could take no cream but some sugar, and the statement I had cream or sugar is true, right? Something like that. The only time you were lying in saying like I had cream or sugar with my coffee was when you took neither. You see that? That's the one time when inclusive or, this new logical operation that we're trying to use to prove whether or not something is true or false, is actually false. That's the one case. In every other case, it was true. Think of it as saying like I had cream or sugar. Inclusive or. Okay? In this case where I took neither of them is the only time where this was a false statement and it didn't make sense and I was lying. Okay? Think of false as in lying. That's usually the best way to think about it right now. Any questions about this table? Any ideas about it? Easy enough to understand? Because that's just one kind of or. We still have the other kind. Let's make a symbol for that one. Why not? Here is exclusive or. Dun, dun, dun. The symbol for that is like a plus with an O around it. I will also say XOR for short. I just took the X out. People like to say it that way. Exclusive or, XOR. If you want to prove that A XOR B is true, then you have to show that either A is true or B is true, but not both. Okay? So here's like A can be cookie, you get a cookie. B can be you get ice cream. And A XOR B, A exclusive or B can be like I got a cookie, or mom saying you can have a cookie or you could have ice cream. Exclusive or. Do we see the main difference? If I flash between these very quickly, do we see the difference? Whee! There's only one part of the table that's changed. The top row. Whee! Right there. That's the main difference. So this is saying that it's okay to have just a cookie and no ice cream. That means I had a cookie or ice cream was true. And it's okay to have no cookie but some ice cream. Still the statement, I had a cookie or ice cream is true. Exclusive or. But now, because it's exclusive, I can't do this part. I can't have a cookie and ice cream and say I exclusively or'd had a cookie and ice cream, right? That is now false. That's now lying to mom, yes, in terms of exclusive or. And still, down here, it's false as well, right? You can have a cookie or ice cream. Me saying, hey, yeah, I did have a cookie or ice cream. When I had neither again, still false, right? I'm still lying. In this case, I stole extra food. In this case, I had nothing. Maybe mom made both the cookie and the ice cream, and now she's sad that I didn't have anything, okay? So think about falsehood as someone is lying to you, okay? I'll just write this down here. Think about, if only I could spell think. Think about false as in, think about false as someone is lying to you. Okay? And that should help. Any questions about exclusive or? And the key difference is that one part right there. True became false. Can't have both now. I hope we see how useful this can be, because now I can just use these symbols and it's very clear to whoever I'm talking to, like, okay, yeah, it's that kind of or. Whereas it could have been the other one. Yeah? So that's why we have math for this kind of stuff. Are we ready for the next one? This one makes the most sense. This is and. It corresponds exactly to the and that we have in English, which is nice. So this is a logical operation called and. The symbol for it is the upside down little v, so we call it a wedge, and so it's A and B. We draw it like that if you want to get fancy. And is just saying you have both, right? Like, I have cream in my pantry. I have sugar in my pantry. It's available to you. If I tell you that I have cream and sugar available for you to have, if you would like, The only time I'm not lying to you is when I really do have both sitting in my cupboard, right? To prove that A and B is true, you have to prove that both A and B are both true. It's the only time. The only time you're not lying when you say, yeah, I have this and this. In every other case, you're missing something, right? If I just told you, yeah, I got cream and sugar waiting for you, but you only had cream but not sugar, then that was a false statement. You were lying to me. Yes? Same with the flip-flop. Boop, boop. Still false. You just had sugar. And finally, if you had neither, you're definitely lying still, right? That was a false statement to tell me that you had something and something else, but really you had neither. There's only one way to make an and true. Only one possibility to make an and true. And interpret this as like, we have cream and sugar. Let's see if it's false or not. So that's and I just want to point out something cool and mathematical, maybe beautiful if you're into this kind of stuff. There's only one way to make and true, and there's only one way to make or false. That is magical. It's a very powerful concept. These two operations are linked in a very special way that if you get into a upper division logic class, you will learn about. It's called duality. But yeah, there's a very, very strong link between inclusive or and they're called duals of each other. Feel free to look up that on Wikipedia. It's very cool. But any questions about the and operation? All right. Again, just helps us specify things logically so that nobody gets confused. Okay? The last major operation that I care about you learning before we talk about some minor ones is the not operation, also called negation. And this one, it has a symbol. You could just spell out not as usual, but the symbol looks like this. It's like to me, it looks like a diving board. And so that's kind of how you can remember what it does. Like, think of a person on the diving board about to like jump off and do a flip, because what not does is it flips true to false, and it flips false to true. Isn't that cute? So you just have to show the opposite. To prove that not A is true, the negation of A, you just have to show that it was false. Okay? Show me that it was inverted. It inverted was true. Okay? So true becomes false, not true is false, not false is true. Okay? Does that make enough sense? So this is like saying, we don't have cream or something. The don't is the negation. It's like, not cream is true, right? And so the only way for that to be true is if, yeah, you really didn't have cream. That was a true statement. Yeah. It's a bit backwards, but I hope that makes enough sense. Let's see here. What do I want to say next? I think that was the gist of it. Any questions about negation? It only takes one thing. You negate a single thing, whereas all these other ones, they took two things. They were called binary operations because they took stuff on both sides. But negation only took one thing. It just inverted one true or false value that you gave. Something slightly different, right? Yeah, if we're okay with this, what I'd like to show you, or just tell you now, is a very interesting fact that makes it very powerful, because actually all these operations, if I want to give you a secret, all of these operations are the reason we have computers, in fact. The inclusive or, not, and you can build a computer out of just those. And true and false is just the ones and zeros, right? Crazy enough, that's all you need. And a little clock that goes on and off a little bit, a lot of times a second. You can build a computer using just those operations. And we have a PowerPoint and a projector, and it just all comes together. It's really cool. So yeah, you can express every fact, every possible truth table with some combination of and, inclusive or, and not. So you might have a bunch of variables, A, B, C, and D, all these propositions that might be true or false. And then you have some final thing that you're trying to prove or show whether it's true or false in every case. That's your cloud over here. And maybe it goes like, okay, it's got to be true in this case, false in this case, false in this case. No matter what you put here, whatever combination of trues and falses you have, and as long as it needs to be for every possible variable, you can make this truth table, this output, using some long, maybe, combination of and, inclusive, or, and not. Isn't that cool? So you'll have to wait until CSCI 26 if you're a CSCI major to learn more about this, but I thought I would tell you it now. Isn't that awesome? Any questions about that? That's a fun little fact, I think. All right, and I might as well show you, or at least give you a hint, make it intuitive as to why this might be true. So let me show you. I just told you that it's inclusive or, right? And inclusive or and not. You can express every possible truth table. So there better be a way then to express exclusive or without exclusive or. Ooh, let's do that. I need this combination in that order. Let's make it happen. Let me show you. So I'll give you the answer, but I want you to take some time to fill in the table. I'll give you a few minutes to work on it, but I'm going to get you started, of course, because you don't know how to start a truth table just yet. That's okay. So I'm going to construct exclusive or using and, inclusive or, and not. And here's how you do it. A exclusive or B, that is, in fact, logically equivalent to not A and B, or A and not B. And if I tell you this in English, if I read this to you in English, it might make a little bit of sense. So yeah, A exclusive or B is true if A is false and B is true, or A is true and B is false. Not both, though. So this is the same. So we're going to make a truth table and spell it out why this is true. Okay? So here's how you do it. You start with your variables on the left. So here's A and B. And then you give all the possibilities of what they could be. So A and B usually goes true, false, and true, true, false, false. And so now we have what A and B are. And then we're going to build up all this stuff. So remember that we need to eventually have a truth table for just this. So we need to build that out of not A and not B. And then we need to and some things together. So we can just do that piecewise, just small steps at a time. So I'm eventually going to need not A, so let me make a row for that. Or column for that, sorry. So here, let's have a not A row. Let's have a not B row, because I'm going to need that too. And then I can make the bigger things, right? Now that I have like this and this, I can and them together to make this whole thing. So let's have a row for that after this. So I'll have a row for not A and B. And I'll have a row for A and not B. And you know you can get this by using the and operation on this row and this row once we fill them all in. Okay? And then after that, we have both of these. I can OR them together to get the whole thing. And then I'll show you that it's the same as exclusive OR. I'll have a row for the final thing now. Not A and B, or A and not B. And there's no easy way for me to give you all of the truth tables. So the best thing I can do is go into Discord right now. If you want to open Discord on your computer or your phone or whatever, I can give you the screenshots of all these little tables that will be useful to fill in this. So that's the best I can do right now. That's where I'll go. Once my Discord starts up, that is. It is made out of JavaScript after all.
Where do you want us to make it?
Oh, just on a piece of paper. You don't have to turn it in or anything. Sounds very hard to type, but yeah, just think about what it should be, and then we can come back and talk about it. Boop. And here, CSCI 1. So yeah, here, let me just give you these screenshots of OR. You need OR, you need and you need not. There we go. So that's the best I can do. Sorry, you have to flip around between places. But now I can have this slide up and you can look at the others. So let me fill in some of these rows, like not A. We have to fill this in based on A. So let's negate the A. Every true becomes false. Every false becomes true, right? So here is true. Let's make it false, right? That corresponds. It's false here, so it must be, or sorry, true there, so it must be false here. It's false here, so it must be true here. And that's a horrible looking F. Boop, boop. So that's not A, and not B is very similar. It goes false, true, see? True becomes false, false becomes true. That's always the B row that I'm negating right now. False, true, and I'll do one more for you, and then I want you to do the rest. So let's do not A and B. It's only ever true if both of those are true. So I got my not A and I got my B. And it's only ever true if both of them are true, which is only right there. You see that? That's the one row where it's true. The rest, there's at least a false somewhere. So this is the only true row and the rest are false. Boop, boop, boop. Let's just make sure I'm doing that right. False, false, true, false. Yeah. Seems to be right. So I want you to try these. Fill in these two rows, please. And please discuss with your neighbor as much as you need to do. But figure out what these four things should be and these four things should be. And then we'll come back and discuss. And let me know if you have any questions. Remember, they line up. Like if you're filling in this one, you can only consider this row. All right, does anybody need any more time? Did we get it? Still working? Which one? Who needs more time? Okay, that's fine. You got plenty. What I can do in the meantime is draw the last row, because we want to show that this one is equivalent to A, X, or B, and we know what that should be, right? So let's draw that over here in rainbow. So it was always, it's only ever true if they differ. So those two cases. So false, true, true, false. And our hope is that these are all the same. Show that they are logically equivalent. You could write one or the other, doesn't matter. They do the same thing. All right, are you ready to go over it? Okay. Let us do it. So let's do this row. I like that. This is the and. I'm anding together A and not B. So I'm working with this row and this row. That's why we made this extra helpful row for us. with the not be. We don't have to think about it. Now we can just do our and on both of those. So now it's true and false. Well, that's definitely false, right? Because one of them is false. An and is only ever true if they're both true. That's false. Then we have true and true. Ooh, that one's true. Nice, nice, nice. We have false, false and anything. I don't even have to look at this row, right? It's automatically false. Same with this one, false and true, still false. It's only true if they're both true. So now I have this row, and I can OR them together. An OR makes a true whenever there is at least one true. So these two are false, false, or false. If we go back and we check the table, it's the only time it's false, sadly. So we get a false there. False or true, one of them is true. So the whole thing, one or the other, or both, yeah, the OR is true. Same for this one, and false for this one. And what do you know? This is equivalent in every case to exclusive OR. So this is exactly the same. Isn't that neat? So you really only need these, and, ors, and nots. In a special way, you can make anything. That's my hand-wavy proof to you of that. Are there any questions about this? About how you do the table, why they're equivalent, anything like that? I think that's magical. Very useful, because you only need to build 3 different kinds of circuits, right? That each do one of these things. You just mass produce those, nice and cheap. Make any logical function that you want. So if we're all right, I have 2 more logical operations that I want to teach you about, and we'll go from there. So I actually lied when I said you only need to produce those 3 operations as circuits, and then it'll save you a lot of money. Actually, you only need to produce 1 kind of circuit, and you can combine just that one in special ways to make every possible one. So let me teach you about Nand and NOR, all right? Just a weird abbreviation. So Nand is equivalent to the negation of A and B, okay? Not A and B. And NOR is the same but for OR, so the negation of A or B, okay? So here's A and B, flip them all, that's Nand. Here's A or B, flip them all, that's NOR. It just so happens that just like the combination of and, or, and not, making every possible Boolean function, we say, any possible truth table, Nand alone or NOR alone can also do the same thing, crazy enough. So this process, this idea of making every possible truth table, that's called functional completeness. So this set of 3 operations is called functionally complete. These are functionally complete. But if you think it hard enough or look at the Wikipedia page, Nand just by itself or NOR just by itself is also functionally complete. Yeah. So same for NOR, just by itself. So really, if you just make a circuit that does NAND, maybe you've heard this word before in terms of CPUs. If you just make a circuit that does NAND, just make a few billion of those, put them together in a special way, and you have a CPU. That's amazing. You only need 1 Boolean operation. You can make any possible truth table. But deep down, it really was a combination of and not. You can make OR out of that, apparently, as well. Okay, so are there any questions about this idea? It might seem mind-blowing. I don't have the proof for you, but Wikipedia does. It builds all the other truth tables in terms of NAND or in terms of NOR. But it's cool to think about. All right. So I think I just have a few more examples for us, and then we'll talk about actual circuits. So are we good to move on? Have some more examples? Okay. Well, let's do it. here is an English statement. And I've helped you by drawing some parentheses, of course. But here's the idea. I'll give you $20 if you clean the bathroom and, in parentheses, mow the lawn or do the dishes. And let's let this be inclusive or. And like this is supposed to be a proof. This is supposed to be a true statement. Let's make sure we're not getting cheated out of our $20. So let's figure out all the conditions under which we are guaranteed to get our $20. Okay? We want to find a way, maybe the easiest way if we're lazy, to get the $20 out of this statement. Yeah? So the first thing we do with this example is we translate it into logic. Let's just say clean the bathroom. Let's make that, let's call that A. Let's say mow the lawn is B and do the dishes is C. So really, this is asking about the formula A and then in parentheses, right, B or C. Yes? And then we can just draw the truth table for this and find all the ways that it could be true and then maybe pick the easiest one or something. I don't know. Or at least look at all the possibilities. Because assuming this is a true statement and we're not being lied to, and as long as we fulfill this and make it true somehow, we're going to get those $20. Okay? Let's do it. Let's make a truth table for this formula. So that's, again, A and B or C. And I encourage you to try writing it along if you like to write quickly, but let me walk you through it. A, B, and C. This is good practice, at least. So now we have 3 variables to try all the possibilities for. So let's have 3 columns. I always get those messed up. Let's have 3 columns for each of them. And because there's 2 options for each of them and 3 columns total, 3 variables total, we have 2 to the 3 outcomes. And here's like the standard way of drawing it. It's always, this one alternates true, false, true, false, true, false, true, false, true, false. And then this one also, then the next one alternates true, false, but every 2 now. So this one goes true, true, false, false. As long as you cover all your options, it doesn't really matter, but this is the standard order. True, true, false, false. And then this one alternates true, false every 4. True, 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 true. Let's try and line them up at least. And then false, 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 false. And this magically generates every possible option. If you consider false to be 0 and true to be 1, we're actually counting up in binary, if you care about that. We'll learn about that later in the class. But that's a good order. So we're like counting down in binary in a sense. Now we can just fill this in. Let's do the B or C because we need that row. And by row I mean column, of course. And then we'll do the total. All right. So B or C. Then we'll have that ready to go to use in the final one. A and B or C. All right. Okay, so B or C. I have true or true. What should this be? Yeah, thank you. I appreciate the audience participation. So it's always true if one of them is true. So, for example, this one down here, false or false, that's false, right? That's the only time. So the rest of these, okay, there's one true here, true or false. False or true. Still true. This is false or false, though, so that one's false. And then we can do it for the rest. So that's true, 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 false. Interesting. A little pattern there. And then we can AND with A, because we just did this side. We made a whole column for it. And then we'll do A here. Okay? We'll AND it with A. So this ANDed with this goes here. So true and true. Oh, that's also true. Nice, nice, nice. True and true. Again, true. One more true. And then this one's false because it's true and false, right? Boop. And then, what's the answer for all of these? Yeah, because this is all now false down here. False ANDed with anything is false. False, 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 false. Any questions about how I got this? I'm just reading off the tables with enough experience, but not too bad, I hope. So it looks like there are only three ways to get $20. Either we could be really, really good people and do every possible thing, or if we were lazy, we really can notice that we didn't have to do both B and C. We could just do one or the other, right? Because that's what the inclusive or implies. So maybe it's easier to do the dishes, and so we'll pick the third option, and we're still guaranteed to get the $20. Okay? So that lets us cover all our bases and see what the possibilities are. Yeah? Now I have one for you. So, go off. Definitely, this is a piece of paper exercise. Help each other. Let's make a truth table for A and B, or B and not C. So that's a big one. All right? I'll get you started with the ABC bit, because I want us to all have at least the same order there. And then I want you to do all the rest. If I was smart, I would have just copied this from the previous slide, but I'm not. So this is true, false, true, false, true, false, true, false, and this is every two, true, true, false, false. And this is the standard order so that we can compare our answers. True, 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 false, 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 false. And so now I want you to do the rest, end up with a truth table for just this last thing. And it looks like as intermediate stuff, you're going to need A and B for that left side of the OR. You're going to need not C, because that'll help you make B and not C. And then finally, you'll have the rest of that ready to go. You can do A and B, or B and not C. Yay. All right, so take a little while to get started on this, and then I'll start filling it in too. Okay, I'll give you a head start though. And please yell at me if you have questions. Give you like another minute head start.
I just got right down on the board.
Oh, nice. Maybe 2 minutes then. All right, let me fill in some of these for you. So A and B, it's going to maybe repeat now. In a weird way, it will repeat. So true and true, true, true and true, still true, true and false, true and false. Oh, that's two falses. False, false. And then the rest is false, right? Because A and B is false here. So I got 4 more falses. And so really, it's technically the A and B truth table where you got like sets of 2 somehow. It's weird how that worked out. And then we have not C, so it's just all these flipped. So false, true, false, true, false, true, false, true. And then we have B and not C. So I just made this one the not C, and then I have B to and it with. So let's just make it easier on ourselves and find all the true cases. So here's true and true. That one's true. Those are false, not worth looking at. You guys can see my notes right here. Here's true, possible, true, and true. So right there as well. And those are the only 2, right? Let me just confirm that. 1, 2 ways of making it true, and so the rest are false. So always try and find the shortcut if you can. So now we have that, and now I can take this guy, and I can OR them together. And now I have true or false in each case. So it's true if any of them are true. So I got trues over here, so I got 2 trues to start. And then kind of out of luck for the rest of these. It's true if the other one's true in that case, which makes it only true right here as well. Yes, so one last case. It's the third way of making it true, and so the rest will be false. False, false, false. False, false. And I found 2 ways, or 3 ways, sorry. 3 ways of making this final statement true. And depending on what this means, that will help us determine which of these universes we want to be in, assuming we want it to be true after all. Okay? Everyone get this with enough work? Any questions about it? All right. So, yeah. We are good, though. I'm about to switch to something similar yet different enough. All right. Let's talk about logic gates and circuits. This is exciting as far as we're going to get into this in the class, but very, very useful stuff. This is what computers are made of. So this will answer the question of like, yeah, this logical stuff is super cool. Now I can order at a restaurant properly. But how does this help me in computer science? Because this is a computer science class. Well, let me tell you how to build a computer. You can make circuits to do all of these operations, right? All of these operations on true and false. And to a computer, it's all electricity, right? 1 is true, and 0 is false. And, well, true or 1 is high voltage. It's like 5 volts or so in most circuits. And then false is low voltage, close to 0. And then we can build, out of transistors, these really cool things. They don't look like this in real life. That's just how we draw them when we're building schematics. But we can send information in on some wires. This is the AND gate, right? It performs the AND operation. We can send information in on these wires, a 1 or a 0, a true or a false, because it takes 2 things. And then it will AND them together. And the output wire will be sending along it the results of A and B. Ooh, that's nice. And this is what these all look like. This AND looks like, I don't know, one of those bullets in Super Mario. The OR is a curvy version of AND. The NOT gate is a little triangle with a dot at the end. It's like the dot is where the negation happens, is how you think about it, because it makes the rest of these make sense. And a not is also called an inverter. So this takes in something and outputs the negation of that something. Not A is coming out of this wire. Okay? So there's and, or, not. Nand and nor are drawn like this. First the and, then the not. First the or, then the not. And then exclusive or looks just like or, but it has an extra little line right there. That's how they differentiate it. So you can build these all out of transistors and make these circuits. Any questions about, like, what's going on? Like, if I put a bunch of these together, would you understand what it's going to output? Let me give you an example, and then I'll have you try. Let's do this. Not A and B, or C and not D. Let's make a circuit using these to perform that operation and have one last wire coming out that has this result running along it. Okay? That's the goal. So we have 4 inputs, A, B, C, and D. So we need 4 wires at the start on the left. That's important. Okay. This holds A, B, C, and D. So I got that information coming in. And what do we need to do? Well, let's do this one. I have to negate A and then AND it with B. So I need to negate this A before I AND it, right? You see the order of operations? That becomes very explicit in the circuit diagram. So in order to negate A, to do the not, I need to draw this. I need to draw a not gate, or an inverter. Same word. So I'll draw a little triangle and a dot. And so now coming along this wire, I have updated it. It is now holding not A. That's how you read these, okay? It's always from left to right. And then I can take that not A and AND it together with B using an AND gate. So here's my AND gate. Looks like one of those bullets. So I'll draw one of those. Whoop. And take the B. Doesn't matter what side it's coming on, but it works out in this case. And now coming out of this AND gate is not A and B. Do you see how I'm reading this? Does that make sense? All right, so let's do the same for this one down here. C and not D. So I need to negate D so I can AND it with C. So let's negate it. Now coming out of this wire is not D. And then I'll AND that with C. Boop, boop. With an AND gate. And so coming out of here is C and not D. Yes? And now I just need to take those two sides and OR them together. So let's do an OR gate. That looks like this. You draw it like that. OR gate time. One last one. Let's put it here. Boop, boop. And now finally, I have what I wanted. Coming out of this wire is not A and B, ORed with inclusive OR, C and not D. And that's exactly what I wanted. It doesn't tell me when it's true or false, but if I sent some electrical pulses through those wires, and this one was connected to a light or something, then it would make the light shine if it was true, for example. Have some switches, make it all cool and physical. Totally possible. You'll have to wait until CSCI 45 to do that, but it's totally worth it. Any questions about how I got from this idea to this schematic, this diagram? I'm about to ask you to do it yourself. All right. I'll give you a head start, but I'll race you, and we'll do this one together. Or maybe I'll give you some time. Doesn't matter. Do this one. Make a circuit for this. B or not C, and not A and D. So, again, let me give you this. All these logic gates on Discord. That's the only place I can give you a second thing. Sorry. If only we had 2 projectors. And here's what I want you to do. Or maybe I can, for a split second, just put it on this slide, can I? Why not? That works. So yeah, take a little while and give this a try, and then I'll do it with you. I'll delete this. All right, are there any questions? Or are we just drawing away? Another 30 seconds, then I'll start doing it. All right, so I'm gonna make this go away so I can draw. So again, we need 4 wires. Probably easier to not put them in order, but that's okay. First, might as well work on the left. Let's OR together B and not. Yeah, we're ORing them. And I used the word and, I got scared. B or not C. So first, in order to OR with B, I need to create the negation of C using a NOT gate. And then I need to OR that with my B. Just like that. It's supposed to be coming to a point there. That's the OR gate. So that goes up in there. And then I want to AND this whole result with not A and D. So let's see how we're going to do that. We need to negate A, right? So this needs to be negated. And then I need to AND that with D. So this is running along. I don't want to deal with that wire, so I'm going to hop over it. This is how you draw that in a circuit diagram. You just draw a little circle like that. You're hopping over that wire. And so now I have not A and D that I can AND together. Whee! Best drawing that I can give. And then the final result is this ANDed with this. So an AND gate again. So this side, this wire is holding B or not C, and this wire is holding not A and D. And the last thing we need to do is AND them together. So this final wire holds the answer, right? I'll just call that answer. Any questions about this? Yell at me if I made a mistake. I think it's correct at least. But we got some NOT gates to negate. We got some OR gates to do the OR of, just one, and 2 AND gates. Okay, see the difference? It's sometimes when you're first learning, hard to tell the difference between an OR and an AND. Probably that curvy back bit is the easiest giveaway. Okay? Any last questions about this? If not, you can go a whole 2 minutes early today. You're welcome.